Okay, so I said that I was going to go and to make some videos about how different data structures and algorithms would work. And so I thought I start with union find data structure, or often called disjoint set. And let me just make sure that my writing tablet is connected. All right. So um, I just want to go through first of all these what this data set is, what does it do, and then I want to talk about how it's implemented internally, and then maybe and also the complexity, although I would not really be doing a formal complexity analysis because it's actually not that easy. All right, so what is the disjoint set data structure, or sometimes called union find or merge find set? It is a data structure that stores a collection of disjoint sets. Okay, so equivalently stores a partition of a set into disjoint subsets. So what does that mean? It means that if you have a bunch of objects, n of them usually, you keep track of who it's this separate this whole set into a bunch of subsets where everybody is in some subset, and some subset will have one, some will have more, and of course there might be empty set, but empty set we don't worry about it. But what else can you do? You can also decide to add new sets, merge them. This is the union or merge operation, and also finding a representative member of a set. So what means that if you have an item, you can find out which set it belongs to, and the ID of the set, it's one of the members. Okay, and it's always the same member. So if you ask multiple members in a set who which set they belong to, it will always return the same representative. So the last operation makes it possible to determine efficiently whether any two elements belong to the same set or to different sets. So you ask the representative members of two different elements and they both return the same, then you know they're in the same set. And if you get different members, then you know they're not the same set. All right. So basically the three operations you have to do would be initialize into what we call singleton sets. So meaning that everybody is in their own set. We need to be able to, it's usually called find X. What does it return? An ID of the set containing X. And it's always the ID of the member of the set. Although if you have multiple members, it can pick any one of them, but it will always pick the same one. That's the important part. And then finally, you can merge or union. It merges the sets containing X and Y. Now, there are two things that I need to point out. First of all, the first one, I guess it's obvious. If X and Y are already in the same set, then this does nothing. Okay, but if you just depend on how you decide to implement it, you still have to make sure that you check for that, because if you do the operation blindly, maybe you mess up the internal structure. So usually it contains a check to see if the two things are already in the same set. Okay, but anyway, and then the next thing is, if you have something like this, let's say X, Z in a set, and Y, W in a set, then when you merge X and Y, remember that we're not just merging X and Y, we're merging the entire sets into all of them. So after this operation of merging x and y, if somebody were to ask, are w and z in the same set? It would say yes, even though w and z are never directly merged. Okay, so when you merge them, this is um, indirect. All the things that are indirectly attached are also merged. Okay, so there's three different. So we already say, the word disjoint sets. There's another word called union find or merge find, and a third name for this kind of data structure is sometimes called dynamic equivalence relations. So if you have taken Math 2000, the equivalence of relations are relationship between two things in a set so that x is always related to x by itself for all x. If x is related to y, that implies that y is related to x for all x and y. And if x is related to y and y is related to z, then x is related to z for all x, y, and z. So um, the fancy words for this is called reflexive. This is called symmetry. And this is called transitivity. Okay, the exact words are not that important, but if you have learned equivalence relations, you probably have seen these words. And the relationship of whether two things are in the same set is it's an equivalence relation, right? So an element is always in the same set as itself. If one element is in the same set as, if x is in the same set as y, then y is in the same set as x. And finally, if x is in the same set as y, y is in the same set as z, then x and z are also in the same set. Why is it dynamic? Because as you call merge and merge things together and then call find, find will return the current relationship between objects. Okay, so it's dynamic because you don't just say here are all the relationships at the beginning and then just do a lot of queries. Rather, you can dynamically update this. Now, another way to think about it, if this was not dynamic, would be simply to have a graph, an undirected graph, because this relationship is symmetric, an undirected graph that will just have an edge between two elements if they're related, and then it turns out that a connected component is just the set. Again, if you have seen equivalence relations, you might have heard of the word equivalence class. And this would be basically equivalence class are all the things that are related to each other. And if you look at the elements of the entire set of interest, the entire set of interest will be partitioned into equivalence classes where every class contains elements that are equivalent to each other, which is basically our disjoint set. So all of these things are related. And why am I telling you this? Because if you're looking at things that you say, oh, this looks like a equivalence relations, or maybe some other things, having different terminologies can sometimes trigger your mind into realizing, oh, wait, this is the one, this disjoint set or union find is the one to use. All right. Now, how are these things implemented, right? So generally, we have to decide at the beginning how many objects we want. Okay, so at the beginning we have to say, here's our entire set of n things. I want to keep track of them in this algorithm. Okay, so that's the first thing, and then you have the three operations. Now there are many ways you can do this, but if you just, for example, I don't know, use a graph, let's say, and then whenever you merge them, you just draw an edge. then every time we do find, you might have to do a depth first search or something to figure out where everything is, who you're related to, and which one it's. And then when you merge them, you don't just draw an edge. You have to somehow reassign the labels so that everybody has the same ID, right? So, for example, if you decide to merge, I don't know, merge 1 and 2, if everybody just stores an ID, right? So at the beginning, I'll use 1 based. Everybody stores 1, 2, 3, whatever, like this. This is my ID array. And when you merge them, well, then I just say, okay, let's just make both of them 1. Okay, so just write this 2 to 1, and then great. And then you merge 3 and 4. So you make both of them 3, let's say. But now the issue is, if I try to merge 1 and 3, I cannot just write this 3 cannot just overwrite this with a 1, because what about this other 3? Right? And in general, even though I want to overwrite the ID for 3, anything that has the ID of 3 needs to be overwritten too. And I would then, if I use this representation, I would then have to scan the entire array to replace the 3's by 1's. And as the sets get bigger and bigger, and if I try to merge things this way, and I have to always go around and replace all the labels of one by the other, that could be a very costly operation. I might have to scan the entire array to find all instances of 3's. And so I don't like that. So what can we do instead? Well, I'm first going to draw a picture, and then I'm going to also show you how we can represent this. So again, I'm just using 1 base. 0 base, of course, is similar, and you can figure that out. So I'm going to have n objects like this. And for every object, I'm going to have a parent pointer that points to itself. This is my initialization. What is this pointer supposed to be? Pointer is supposed to be to somebody else that's in my set. At the beginning, there is nobody in my set, so the only place I can point to, it's myself. And the way that I'm going to do find, the find operation basically just starts at x, follow pointers until we loop. Okay? If you don't like the loop, I guess you can, I don't know, point it to null or 0 or something. But anyway, you point it until you follow the arrows until you can't follow anymore. That's basically the idea. Okay, so at the beginning, if you just do a find, you right away you see that you come back to yourself. So return the last ID that you follow before you either loop or you know, if you decide to point them to null or something like that, then you do the same, but you return the last ID that's not null. Okay, so in this case, right now you just return itself because you hit the loop right away. Now to merge, what do? You find X and you find Y and call them ID1 and ID2. And assuming that they're not the same, okay, so of course if they're the same, then you're already in the same set, so don't do anything. But if they're not the same, you'd say the parent of ID1, it's ID2. So what happened is, let's say I merge 1 and 2. 1 and 2 originally were pointing to themselves, and I am going to merge ID1 is 1, ID2 is 2. I'm going to reset the pointer of the parents of 1 to point here. Okay, so now if I were to find 1 or find 2, both will return 2, although for 1 it will take at least one more step to get to 2. Okay, so later on I would merge 3 and 4, and I would have a similar structure. And now if I were to merge 1 and 3, now why do I have to go find first? Because if I simply sever this link and point the parents of 1 to here, 1, of course, will get to the right parents, which is 4 eventually, but 2 and anything that 2 might point to, it's now severed. 2 is like just hanging by itself, and you'll get wrong reset. So instead, what we're going to do is we're going to find the representative of 1 and 3, which it's 2 and 4. So actually, ID1 is 2, ID2 is actually 4. We don't merge 1 and 3 directly, we merge 2 and 4. So we're going to end up pointing this one over here like this. And now, doesn't matter which one of these we start calling find 1, 2, 3, or 4, it will always eventually end up at 4. Okay, so that's the very basics of union find. Everybody have a pointer, an index, and generally you don't need to use pointers. You can just use an array, and then again, if it's one base, you just initialize everybody to have like this, and then when you set 1 to 2, when you merge 1 and 2, you just set this to 2. When you merge 3 and 4, you set this to 4. And then finally, when you merge 1 and 3, you end up merging 2 and 4, and you just set it up like this. Okay? And if you wanted to find, what can you do? You can write find like this. You can do something like this. So I'm not going to bother with C++ syntax. If parent of x, it's equals to x, then you return x. Right? That means you're in a loop. Otherwise, return find of parent x. So I'm doing it recursively. Right? So if you're looping, you just return it. Otherwise, you just go to the parents and say whatever you are, whatever your label is, that's my label too. Okay, so if we do this, what's the complexity? Right, the complexity for both of these, right? So merge, this operation is simple, right? Just set a point, set one single number. But you do 2 finds before that. And the complexity of find, of course, is the same as merge because merge uses 2 finds. That's the main operation. So whatever the complexity of find is, merge is just 2 times that complexity, which is the same. So how bad is find? Well, that depends. Depends on what? Depends on how long of this path you have to follow. Right? If you have to, if you try to find 1, you have to do 2 steps. If you try to find 3 and 4, you have to have 2 and 3, you do 1 step. Same, 2, wait, okay, maybe 3 steps. 1, you have to follow 3 arrows. This one, and then the loop. So to find 1, you have to do 3 steps, let's say. And then for 2 and 3, you have to do 2 steps. And 4, you have to do 1 step. And basically, it depends on how deep this chain of arrows are, right? If you later on decide to merge, I don't know, if you merge many things, right, then this path can get really deep, potentially, depend on your sequence of merges. Also, here, why am I setting the parent of ID1 to ID2? Why don't I point it the other way instead of merging, pointing 2 to 4? I could have pointed 4 to 2. there is no difference in terms of correctness, but perhaps we can be a little bit more strategic to make sure that we don't get something that grows out of hand. All right, so what are some of the things that we can do? So the main concept, I guess, is to make this, I don't know if you want to call it trees, but so yeah, things like this. You can have multiple things pointing to it. Everybody point to the parents. It's not even just one thing. It could be two things, three things, could be many, many things. And so on. We want to avoid situations where the height of this collection is too high. We want it as short as possible. How are we going to do this? Well, we can actually keep track of the height as we merge. So imagine that we have some chunk of stuff here, and we know that it's a certain height, and we know that there's another chunk, and we know that there's a certain height. If h1 is less than h2, so let's just be concrete, maybe this is 3 and this is 4, if I were to point it this way, then now I will be at height 5 because I took everything at height 4 and add one more link to it. On the other hand, if I point it this way, everything over here at height 3 will go up by 1, but the overall height does not increase. So you want to merge the smaller one or the shorter one into the taller one if possible, because then you will not increase the height at all. Now, when would you increase your height? Right? You cannot just not increase height forever. You have to increase your height if they are both the same height. If they're both the same height, then it doesn't matter which way you do it, it's the same. Your height will always increase by 1. And because you're always merging the smaller one to the bigger one, okay, you can actually prove that the only time that you increase the height is if the two things that you're merging have the same height. And if you have n things in your whole set, this tree cannot be bigger than log n height. And that's an important thing, right? We love log n because it means that for very large n, this is going to be relatively small. So fine is going to be efficient. And then of course we can easily keep track of the height because the only time we have to update the height is if I'm merging two things that are the same size. Okay, so if that's the case, if we do this merging by comparing the heights and always merging the shorter one with the into the larger one, taller one, then we can guarantee that the height is at most this much, which means that all my fine operations, it's also at most this much. This is sometimes called this height idea. It's often called rank, and this is often called union by rank strategy. So this turns my union fine operations into log n each time. And if you do a whole pile of these operations dynamically, it'll be just a bunch of log n steps, which for a lot of times that's pretty good. Okay, you have to have really large n for log n to be too big. Okay, but there's more we can do. Okay, so let's say you have a tree structure like this, right? And you're trying to find X. So what do? You start from here, you follow all the way up, and it took you 1, 2, 3, 4, 4 arrows, following 4 arrows to get to that. Again, it can be longer, but it's limited by height of tree. Now remember, in our recursive implementation, we do something like define X. You have some base case, and then you say if the base case is not true, what do? You return find parent of X, right? So everybody will recursively find a parent of X until this is the ultimate root of this structure. So it's going to return this ID. Everybody's going to get this return. But as soon as as soon as you find out, let's say this one, I now know that this is my root. I can actually make use of that information and reset the link. So if I was ever asked to do this find X again, I would now have a shortcut. It's now constant time. Okay, so what does that mean? If I, for some reason, call find X more than once on this X, the second time and the later time will no longer be slow. I pay this price once, and from now on, I never have to pay this again. But there's more. Remember that in order for me to find this ID, I walk through everybody along this path to the root, and everybody recursively would also reset the link to take the shortcut. So, okay, this is already a shortcut. So when I do this, when I find X, not only is my find X faster, this one is faster, but also anything that's attached to this, even though you never directly find anything in this whole branch, all of them are now shorter. And similarly, anything that's attached to X below are also much shorter. And basically the idea is, yes, there might be a time when you call find X and you have to traverse a long path, but you will only ever have to traverse that long path once. As soon as you traverse that one path, if later on you find X, whether it's that one or anything that's related to that path, everything will now be shortcut and much faster. And this is what we call amortized analysis. Amortized analysis. And what that means is we don't actually look at the cost of an individual operation find, because it can vary a lot. Sometimes you have to pay a lot, sometimes you don't pay at all. But we look at the overall picture. If you do, let's say, 1,000 or whatever, you do a whole pile of these operations, you look at the total cost of 1,000 operations, let's say, and you say, well, yes, it's true that maybe one operation can take 400 steps, but you cannot do that 400 steps many times. And when you look at the overall picture and sum it all up, the total, it's actually not that bad. And so amortized analysis basically says you look at a group of operations, and then you see that the total number of operations you perform over the entire group, what is it? Even though some of the operations individually might be long and some might be short. Now, I'm not going to go through that analysis because it's actually quite complicated, especially if this is something that maybe it's taught in a very senior level undergraduate course or maybe even graduate course. But that's basically the idea of amortized analysis. And so what we usually say is we look at a group of operations, see the total cost, and then divide out by the number of operations, and then you sort of an average, on average, how much time it takes to do this per operation. So um, it turns out that if you use both, oh, by the way, this is called path compression. And when you find cofine and figure out what the root is, you also compress the path along the way to make each of them shorter. And it turns out if you do both union by rank and path compression, um, on average, based on the amortized analysis, each union fine operation hits big O of alpha and n. And what the heck is alpha of n? Okay, so it says the specialized type of addition, union, and fine operation of the wait, sorry. The specialized type of force performs union and fine operations in near constant amortized time. Okay, so if you take the group of operations and then you figure out the total time divided by the number of operations, it's near constant. So it's not constant, but it's near constant. For all practical purposes, you can think of it as constants. So what does it really mean? For sequence of M, addition, union, or fine operations, I guess I never talked about addition, but addition is kind of easy because you just make more, you just expand the array and have the parent pointing to themselves. Okay, anyway, for a sequence of these M operations on N nodes, the total time requires is M times alpha N. So the total time of M operations is M times alpha N. So for each operation, when you divided it by M, it's alpha N, where alpha N is the extremely slow going inverse Ackermann function, blah, blah, blah. Although disjoint set forwards do not guarantee this time per operation, each operation rebalances the structure by tree compression so that subsequent operations become faster. As a result, disjoint set forwards are both asymptotically optimal and practically efficient. So it's the best of both worlds. It's not just great complexity but impossible to implement, but it's actually extremely easy. Okay, so now what the heck is this inverse Ackermann function? Okay, so there's like a whole pile of things. What is an Ackermann function? Ackermann function is something that uh, it's a recursive function that looks like this, and it grows extremely fast. So it's a two-dimensional function with a to a4 comma 2. It's this huge gigantic number. Okay, but it's the inverse of that. And if you have a function that grows extremely quickly, that means the inverse grows extremely slowly. Okay, so there's a whole pile of stuff. To be honest, I don't actually even know too much about the Ackermann function. I almost always know about the inverse. Um, in fact, alpha of n, it's less than 5 for any practical input size of n, since A44 is this gigantic number. So basically, okay, without saying, looking at what alpha n is, you can pretend that alpha of n is a number less than 5. There's no practical size of input where this is alpha of n is going to be bigger than 5 or even 4 or whatever. So that's why we say that for each operation, it's near constant. Okay, and then you see it's amortized, right? Okay, so I want to show you in my code library. Here's an implementation of the union fine data structure. It's a class. We'll just look at the public section perhaps first. Maybe I look. So basically, I remember for each element both the parent, which I call P, and then the rank, how tall that set is. I remember how many there are. Oh yeah, okay. Hey, the private section first. So how many there are? So that's my n, and then an array, which is allocated dynamically, so it's a pointer, right? So like this. And initially, I would um, set everybody to point to themselves as parents, and then rank it's 0 to height. Well, I guess I can set them to 1, but it doesn't matter what I initialize them to, because all I care is that I know which one is taller. For find, this is basically what I set. So if we find x, I have an internal function that, of course, need to find using the this parent array. And then for merge, I call find to find the two IDs. If they are the same, I skip it all the way to here and just return false. So I just tell you that false means that I didn't actually merge anything because they are already in one set. Then if they're not the same, then I set the smaller one, right? So res2 is the one that is shorter. I set that to point to the bigger one. Otherwise, it doesn't really matter which one I point to. Um, and then if they happen, sorry, otherwise, so if res2 is the smaller one, I point res2 to res1. Otherwise, it could be that res1 is smaller, or it could be that they're the same. So I point res1 to point res2. And if they are the same, then I update res2's rank to be one more. Now, I didn't bother updating res1 rank because actually I'm never going to use that rank again. I only use ever the rank entry of the one that is the representative. And once I merge it, it will never be used as a representative again. And then here, right, this is my find. If I'm not in the base case, I call find recursively, but then I also set my parent uh, to do the shortcut, and then I return. Okay, so that's union find. Now, um, I do want to show you a different implementation, which is the one that we take to the World Finals or North American Championship. Um, and here you see that it's really short. Okay, so it has no comments or anything because in this more advanced level of competition, there's a page limit on how much we can bring in our code library. So this was kind of optimized, right? So we have a vector. Instead of using a dynamic array, we use a vector. Um, this is the constructor. It initializes the vector, initializes the size, and then this initializes the whole vector. Iota is a function that initialize everything starting 0 and then the next element 1, 2, 3, 4. Basically, every element is one bigger than the previous one. So this basically is a shorthand to initialize everybody to be 0, 1, 2, 3, and so on. For find, uh, this is a shorthand, right? So if A and its parents are the same, then I return A. Otherwise, I return whatever the parents is, but not before I also set the parents of myself to do the shortcut. So this is path compression. They have one more function that does if two things are connected on the same set, right? So this is just checking if the find are the same. But here, merge, it just find one, point it to the other. There's no union by rank. In fact, rank is never kept. Okay. Now, of course, if you keep track of rank and all that stuff, you have to write a lot more code. So this is making it shorter. The question is, why are we throwing that optimization away? Because this can actually make trees to grow really long. Okay, because you know, if you never bother to check which one is shorter and they just blindly merge, you could be in a situation you just merge an entirely a really long chain. So why is that? So it turns out that if you only implement path compression, or if you only implement union by rank, but not the other, it turns out that you can actually guarantee that each operation is log n amortized. So if you do only one of path compression, okay, so if you only do path compression, it turns out that amortized on average each operation is log n time. If you do union by rank only, but not path compression, you can also guarantee that things are log n time each time. But if you do both, then I'll just write this. So near constant time. Now, path compression is very easy to write in terms of implementation. Union by rank requires more code. And in a programming context, not only do we, in this level, not only do we have um, a page limit, we also remember that we can't just copy and paste the code. We actually have to type it in from paper. So less typing means faster implementation. In practice, the difference between log n and constant time, especially if, let's say, this constant is like 2 or 3, you need n to be really big, right? Even for n being a million, or you know, log n is 20, and you can't even get to log n is 30 because that would require basically to keep track of a billion objects, and then you probably don't have enough memory to deal with that anyway, or even if you do, just reading the input would kill your would be slow. So in practice, for most sizes, log n and 1 are very hard to distinguish under reasonable problem sizes. And so the team decided that it's simply not worth bothering to take up space in the code library and also to type the union by rank part, and just focus on path compression only, and you get log n. Okay, so anyway, it doesn't really matter if you're just doing copy and paste, then of course it doesn't make sense to not use the most involved version. But if you want to, you know, type in as little code as possible, be as fast as typing stuff as possible, then most likely path compression only is good enough. In fact, I've never run across a problem where path compression is not good enough. All right, what are some applications? The classic one that this is always brought up in an algorithms and data structures course is dynamic connectivity. So if I have a graph of a bunch of nodes, and dynamically I will say these two are now connected and these two are now connected. And then at some point I want to ask, are these two vertices in the same connected component? Right, so maybe I have a bunch of nodes in my graph, and at some point I say, okay, now these two are connected. And then I might say, this one here are connected, maybe that two are connected, and maybe these two are connected. And at some point I might say, this one and this one, are they in the same component? That the answer is yes. Or I might say it's this one and that one in the same component. The answer is no. And where this usually comes up, it's the Kruskals minimum spanning tree algorithm. And of course, minimum spanning tree means that you have a weighted graph where you're trying to connect everybody using the smallest number of smallest total weight of the edges that you choose. And basically, the way the algorithm works is you sort all the edges by uh, length in the increasing order, and then you go through each one of them, each one of those edges, and ask, okay, are the two things that are connected, are they already connected? If not, connect them. Otherwise, skip it. So for example, if later on the next edge that I'm about to add is this one, it will say, wait a minute, these two nodes are already connected, so I'm not going to use it, and just move on. And so for that Cresco's algorithm, you start by sorting all the edges by the weights from smallest to largest, and you incrementally add edges and connect the two. As long as whatever you connect are not already connected. And so in that algorithm, basically you do an initial sorting of all the edges, and then you do your uh, merge, you merge the two vertices that are dictated by each of the edges in order, but you have to know quickly if they are already connected. And this is exactly what union find is good for. And so the total cost would be m times log m, which is the sorting phase of the edges, and then m for each edge. You do this union find operation, which is alpha n, and because we said that alpha n is essentially free, it's essentially constant, log m is the one that dominates. So basically you just sort it and that's it. And so if you don't use the path compression, if you don't use union by rank, then this part, for example, instead of m log n, instead of m times alpha n, it will become m times log n, because the alpha n becomes replaced by log n. But remember that in order for this graph to be connected at all, m has to be at least n minus 1. So m is already bigger than n, so this actually doesn't matter at all. So even if you don't use the union by rank and then just use the path compression, um, it doesn't actually make Cresco's algorithm any worse, at least in terms of complexity. Okay, so that's, I guess, the end of this little introduction to how union find data structures work. And we'll be putting out more videos of other kind of data structures and algorithms. Some you might already seen, so they might be a review, and some you might have never heard of before. All right.